Welcome to our technical demonstration. We are going to show you what we call tooling of tomorrow. And the fun thing is it's here today. The tooling of tomorrow is really large-scale 3D printed tooling. I'm standing in front of our kitting facility here in Springfield, Tennessee. And here we take our vacuum bagging materials and we kit it into all the different shapes so customers don't have to take rolls of film and fit it to a part. It comes in a box ready to go. Right now, this is our temporary home of our large-scale 3D printing machine that we have purchased a year ago and we've been working with for the past year. Behind me, as you can see and probably hear, we'll probably get cut in with certain noises and so on, so I apologize, but this is really happening. That's our new building where our large-scale 3D printer is going to go. That's our center of innovation. And that's going to be ready in 2 months. And we'll be moving our machine from here over to its permanent home. You best know Airtech for our vacuum bagging and composite tooling materials. We've been in business for almost 50 years, producing vacuum bagging films, release films, peel plies, breathers, sealant tapes. You know us really well for that. This facility is kind of the evolution of the vacuum bagging. Again, I said that customers don't want to take rolls of material when they have a lot of parts or big parts and roll it out and make vacuum bags. They want it to come in already in a box, already pre-cut, maybe bonded together so they can just throw this thing out right onto the part. It eliminates error from workers putting the bag on, waste, and time. It saved 20–30% by going to this on labor and errors. So that is the evolution of vacuum bagging from roll stock to our kitting facility. You also know us for our composite tooling. We make the resins and prepregs, predominantly epoxy and benzoxazine. The epoxy prepreg has long process, masters involved, and we feel the evolution of tooling is the 3D printing. So that's why we've gotten into this in such a big way. We have our machine here in Springfield, Tennessee, again, a 10-foot wide, 40-foot long. We also have one in Differdange, Luxembourg at our Airtech Europe facility. This allows us to make tooling a lot quicker and a lot more cost-effective than what's out there now. Why did Airtech, or why do we think we can get into the additive manufacturing market and know what we're doing? Number one, we hired the best people in the industry. And number two, we've been doing extrusion for almost 50 years. When we make our vacuum bagging films, we extrude those on huge extruders. A 3D printer is nothing more than an extruder on a gantry. We know extruders, we know how they work, and we're able to even do modifications on our 3D printer based on our knowledge to make the process easier and safer and much better quality. So we know our stuff there. The other problem in the additive manufacturing world has been the resins for tooling. It just hasn't been well developed. We know resins. We've been compounding resins for a long time, and we've compounded our own additive manufacturing resins as well. So we have a full line of the resins, and that's what we use here in our shop, and it has been qualified at other facilities as well. So we felt we were in the exact right place to be able to get into the additive manufacturing and allow us to be able to move that world further along when it comes to the composite tooling side. So welcome. I hope you enjoy our presentation. You're going to get to see the machine in use, and our director, Gregory Hay, will be taking you through the actual demonstration and showing you what our capabilities are. Again, thank you and welcome to the technical demonstration.
Hi, my name is Gregory Hay, and I'm the Director of Additive Manufacturing for Airtech International. Today, we welcome you to our facility in Springfield, Tennessee, which is the home of our large-scale additive manufacturing facilities and team. So today, we'll give you a look at what we do and how we do it, including a little bit of an introduction to our full product line and our services. Along the way, you'll meet a lot of our team members, which make up about 30 years of experience in large-scale additive manufacturing. And we hope you enjoy learning about the process from A to Z today. Okay, so here we are on our manufacturing floor with our Thermwood LSAM. This particular machine has a 10-foot by 40-foot build volume. And so what that means is we can print a part that's up to 40 feet long and 10 feet wide, as well as 5 feet tall. So on the specs of the machine, we'll give you a little bit more information about how it works and what its capabilities are. This particular machine is set up to have a 200 pound per hour throughput on the extruder, on the printing side, on this gantry right above my head. And so we can set up this machine to print in two ways. So the traditional way that most FDM printers are done, which is referred to as HLP, where layers are stacked vertically, one at a time, to create the shape. Unique to this machine, we also have the VLP option, which means we can actually print sideways. So imagine the part growing towards you as it's being built. And so this allows us to best orientate your part to optimize either the build time, the weight, or even the face sheet thickness, so to make sure we get you the best tool with the best performance in the least amount of time. So this machine does do both the additive and subtractive processes. So the additive gantry being the one that's nearest to us, with the 5-axis milling gantry being on the far side of the machine. So we'll go down to that end of the machine in a little bit once we meet with our machinist to talk about capabilities and how we operate. On the machine here itself, we do already have the bed set up to print our part we're going to be demonstrating today. So there's a piece of what's called beadboard down there, and this is what the substrate we print on top of when we make a part for any application. So Airtech is working on ways to better improve this area, and we have a lot of things coming in this next year to show you how to make this faster and a little bit more sustainable. So the biggest challenge to large-scale additive manufacturing, especially for tooling, is having the right resins that can do the job that they're intended to. So one of the things I'll show you next is our resin offerings. So not only producing full finished tooling for our customers, we're also dedicated to making sure that you, the customer, have access to the same resins to produce tooling the same way we do, with the same results. And most of these materials are now have gone through multiple heat cycles. So we're already eclipsing 250 cycles in an autoclave with our 350 material. But we have many other offerings for all different applications. So let's go take a look at the resin right now, and we'll tell you a little bit about each one and their applications. So we're going to start on this end. This is our ABS material. It's called the S150CF. So we use this in low temperature applications. So things like trim fixtures and jigs, assembly and bonding fixtures, low temperature curing, and even master models. One step down from there is our modified polycarbonate. So this is the C250CF material. And so shares a lot of the same application range as the 150, but offers a much more durable surface with better resistancy to chemicals, as well as better mechanicals in the part itself. Additionally, we can use this for low temperature out of autoclave cures. So we are seeing a lot of use for this in autoclave composite manufacturing for tooling. On the high end, we have our I350CF material. So this is a PEI or Altem modified with carbon fiber reinforcement. So we're seeing this being used in high temperature bonding fixtures, pre-preg tooling for in autoclave, auto autoclave. And so this has been the star of the show for us in a lot of ways. And we have tons of data. So for those of you that are interested in really durable tooling, especially for high temperature applications, this is it. And it offers great performance for tooling applications in autoclave with vacuum integrity and great surface finish for your parts. But we are thinking about this holistically. So we are also looking at purge material. So you need to clean the extruder between these different materials, or at the end of the day. We also have a purge material that we've developed in Airtech, and this is actually from our legacy line of materials that we used internally for many years to clean our extruders for our film manufacture, where you can't have any sort of carbon buildup or contaminants in the extruder. Now we have that same technology and same quality assurance in our large-scale additive manufacturing. So now we're going to look at putting these resins to work, and that starts with getting a service from our customer and start looking at the tooling design. So how do we now take these resins and put them to work on the large-scale additive manufacturing equipment? So we're going to take you over by the machine, introduce you to Robert Bedsole, and he'll give you a little bit more insight on the design processes, as well as how we print and how we design tooling for all different applications.
Hi, I'm Robert Bedsole. I'm the additive engineering specialist here at Airtech. Today we're going to be printing a trim fixture for a fan cowl tool. I already have the geometry here from the design team, and it's been moved into position. From here, it's a relatively simple process of dividing the part into outer surfaces shown here, and then also we have header support structure. You'll notice that there are cutouts here for lightweighting the tool. This print's fairly simple. We have several tool paths making up the outer loop shown here. Won't go too far into the specifics of the LSAM slicing technology, but it's very advanced, by far the best on the market today. I also have a second tool path shown here behind the main outer loop, and then the backup structure, the headers. The software is very convenient in the way that it shows STL models of the exact printed structure, so we can estimate exactly what the part will look like once printed. There you have it, just that simple. Okay, so first step is we're going to load some material. Today's part is a low temperature tool, trim fixture. So we're just going to use Trim 150 ABS. Notice our LSAM, it's a little loud over here. Our LSAM has 2 hoppers. We're going to be printing from hopper 1 today. And we also have the smaller hopper for experimental tests with ongoing materials development that we're working on here at Airtech. So we have our material ready to go. We'll add our wand to the material, and we'll turn the feed system on. And with that, we're loading material. These hoppers run best when they're full, so we have 600 pounds in our dryer, ready for the print later on today. And then final step, go in and set our temperatures. They're already ready to go for ABS, Trim 150. And the heaters are on. We'll come back in 4 hours and we'll be ready to print. So a wise quality step to do before every print is to ensure that our material is good and dry with our moisture analyzer. Gonna empty out any old pellets, make some space in this container. We'll drop some new, fresh, hot material in. A little loud. Close the valve back up. Fresh, hot, probably dry material. And about 1 scoop for our test. seal it up, let it cool off close to room temperature before we actually run the test. And now we wait about 10 minutes before we check our moisture content. Okay, so 10 minutes have gone by. The material's reasonably cool. We're going to start this test for Daltram 150, already pre-selected. Pretty simple process. It says add sample to pan. Oh, a little much. Haven't run this material in a little while. There we go, now we're at our ideal weight. And we should have an answer in about 5 minutes. Okay, so it took about 5 minutes to get our answer, 0.026% for our moisture content, Daltram 150. That's typical. That means we're sufficiently dry, we're good to print. We're gonna walk over here, we're gonna turn the heaters on, and then after an hour goes by, we'll be able to start printing. Let's see. So first we choose the proper melt config. Melt config number 11 is Daltram 150. Activate that. Temperatures show up here. Turn the main heating switch on and wait about 1 hour. We'll be able to start printing. In the meantime, we'll go ahead and do a dry run. Our program's loaded, the right offsets have been loaded, and we just want to verify that we are printing correctly on top of the bead board that's already been screwed down. So we'll do a dry run. You notice our thermal camera there, using that later to verify that we have good quality of our print. So now that I'm satisfied that the print is correctly oriented, I'm gonna send it home. We'll finish waiting the hour, and then we'll start printing. So now we've waited an hour. The extruder's nice and hot. We are ready to load material. First step is come around the hoppers. Again, we're going to be printing from hopper 1 today. So I need to hook up the feed hose, connecting hopper 1 to the extruder. Then we'll go back over to super control. we'll run the load routine. The extruder will drive down to the guillotine, the purge station. Once it gets there, we'll start the screw moving, and then we'll send the material. Good. Cycle start. Screw's now turning. Move to hopper 1 and turn the feed on. And material's now feeding. It's already coming out. Over there, we should go around the you can see our purge material is now extruding. It'll take just a few minutes to push all of it out completely, and then we'll be ready to start printing. Now that we've finished loading our material, pushed all the purge material out, we're ready to start printing. At this point, I just hit cycle start. I always start by pushing out the degraded material at the very end of the extruder. That's usually where we have programmed the zones to be hottest. And one good high-speed push here. Wipe the nozzle tip off, and then we'll drive over to start printing. Because there's some kind of deep features machined onto the print surface, we went ahead and programmed a second bead along the tool surface. And then we have this header toolpath programmed, support structured. It's usually a good idea to double check the bead width. This yellow bar right next to me is a safety stop, so I'm still protected even though I'm in here. If it bumps me, the machine will go on e-stop. The other thing we need to do pretty early in the print is start our thermal cameras. So we can record each layer for quality assurance. Thermal camera gives us high confidence that we'll have good adhesion layer to layer at the program layer times for this particular print. If you want to follow me. We actually have 2 thermal cameras for this print. The tripod you saw as we entered the LSAM, giving us this view here. And there's a second thermal camera actually mounted to the gantry a little bit higher. We'll turn that one on over here at the super control. Here you can see the layers of green. As they say at Thermwood, green means go. This is dialed in so that for this material, whenever the material is the right temperature to print on, cool enough, but not too cold, it turns green.
All right, so now that you've seen a little bit about what happens on the additive side of the machine and the materials going to work, we're going to start taking you over to the subtractive side of the machine. We'll introduce you to Joe Harger, who's our lead subtractive engineer on the LSAM. So he'll start you looking at what we started with over here, the services from the customer, and then also what geometry has been now created by starting with a near net 3D printed shape that Joe will eventually get over here to work with to bring it to its full dimensions, tolerances, and surface finishes using subtractive processes. So with that, I'm going to hand you off to Joe on this side, and he'll walk you through the processes.
Hi, I'm Joe Harger, Senior NC Programmer here at Airtech. What I'm going to demonstrate here is taking a design from Robert down on the print side and process it through Mastercam, creating the tool paths and showing you machining afterwards. So Mastercam is used from the print side to the trim side from start to stop, which allows us to create a consistent workflow. I'm able to take the print design, see it in Mastercam because it is sliced in Mastercam, and create tool paths based off of the geometry supplied by the customer. So we're going to quickly go through the processes that I've used up to this point to create the model where it stands on the machine right now. So you can see the beads here printed, and I'm going to quickly show you the processes that I use to get it to the point. So I fly cut each side here. And what's nice about using the print model in Mastercam is I'm able to go through the processes and see exactly what the model looks like at any given time. So I'm going to go ahead and skip forward to where it sits now on the machine and go ahead and go to the next step along the way to where it sits. So let me go ahead and turn this off so you can see. So this is going to simulate right before I get ready to machine right now. We're going to machine these grooves in here and also the tooling ball hose along with the outside groove. Let me go ahead and select the tool paths that we are going to run for the demo, and I will go ahead and post those out. So we're going to run this right now. So I'm going to go ahead and post this out, the G code. Give it a name. And now we have the G code ready to run. First thing I'm going to do before I do that is we also use NC Simul here to simulate all of our code before we actually run it on the machine to verify that there's no crashes, everything is correct. So I'll go ahead and run that through NC Simul real quick. And you can see here that it should show me exactly what's going to happen at the machine before I run. I'll go ahead and speed it up a little bit so we're not waiting too long here. So this allows me to verify that there's absolutely no chance that I'm going to crash, damage a part, machine something that's not supposed to be there, first time, every time. So now I'll go ahead and load the program at the machine here. Okay, so we've got our program here. I'm going to go ahead and home the machine out. I was just taking it over there to look at my tooling. And I've already measured the tooling, but I'll go ahead and go through that process for you. Go ahead and measure this tool that we're going to use right now. And what it is going to do is measure the tool on our high precision tool length sensor. So I'll go ahead and get that measured. Okay, the tool's been measured, so we'll go ahead and start the program. It's going to go ahead and do a tool change. Okay, while that's running, we're going to go ahead and get the finishing toolpath ready. We're going to go ahead and machine this whole front surface here. And I think I'm going to go ahead and use a morph toolpath on this one. Mastercam allows you to create just about any kind of toolpath you want. So this one here, I think I'm going to, I've got the roughing toolpath simulated here. And I'll go ahead and apply the finishing toolpath to it as well. The same toolpath for the roughing as the finishing. So that looks good there. I'm going to go ahead and pick my geometry here. You can see here I'm picking this curve. So we'll morph from that curve to this curve over here. And I'm picking these surfaces here for it to machine. And I'm going to give it a tool axis control, which is from this chain here. And basically what that's going to do is allow it to pendulum from that chain and work its way along the surface. So I'll go ahead and regenerate that with this one here. I did a 02 step over. The final surface on this one just needs to be about a 32 RMS, so not too worried about the step over. So once this gets done generating, I'll go ahead and post it out, and we'll run it through the simulation and make sure everything is verified. All right, so I've got everything posted out. I'm going to go ahead and run it through NC Simul to make sure everything is good. There's no issues. See here, progress bar. It should be done here just in a second. All right, so NC Simul is going. I'll go ahead and speed it all the way up so we're not waiting too long here. I don't need to simulate every little detail, so I can slide it to end result and just let it calculate behind the scenes. I'm pretty confident in that, so we're going to go ahead and get the next tool loaded up, our finishing tool, and start the finishing pass. Okay, the surface is done, the tool pass is done, so let's go ahead and take a look at it and see how it looks. Surface looks really good. I'm happy with it. We did about 20,000 step over. It looks really good. One last thing I want to talk about is one of the difficulties with machining this material, and that is tooling and tool life. I've been fortunate or unfortunate, depending on how you look at it, to spend the last 5 years machining this material and trying to come up with tooling that machines it well and it has good tool life. We finally came up with some tooling that is giving us extraordinary tool life and surface finishes that are really, really good. So we can go over those briefly and follow me and we'll take a look at them. So, like I said, a lot of time has been invested into finding tooling that is going to last on this material, 20% carbon fill, 30% carbon fill, whatever it may be. You know, we've tried solid carbide, PVD bits, even PCD. You know, you're getting into expensive bits at that point with the PCD, and they're not even giving us the tool life that we were looking for. We finally found this tooling here, and it's given us really, really long tool life, and we're happy with the results so far. And here in the near future, we're hoping to add it to our catalog to offer to our customers.
All right, thanks, Joe. All right, so going back to surfacing, now you just saw the finished tool and the tools we're using to cut these molds and other trim fixtures in this case. Let's show you kind of what the stages look like as we go from the as printed, so just a printed shape, to some basic rough cuts to a fully finished tool surface, what those things might look like. So over here on the table, we have 3 specimens. This first one here is basically a representation of a as printed shape, right? So this is just about what it comes off the machine looking like as it's been printed. So you can see the bead cusps in here. It's a fairly rough surface, but you can see it's very dense. So it's just a typical placard or sample, so just representation. If we're doing some rough cuts on the CNC, you may still have a pretty coarse surface, but you've got a nice flat surface here, right? So not much going on, but you've at least knocked down these cusps with beads over here to get you probably 90% of the way and get closer to your near net shape that you're going to be doing some finish machining to, other details like the scribes or channels or plumbing like Joe was doing on the trim fixture. But when it comes down to the end here, when you want a real smooth surface, like something you may use on a cure tool, we're going to take this and we're going to bench this to tolerance, but also to surface finish based off whatever the customer needs. So in this case, we assumed a layup tool for curing of a composite part, so we went real fine in the finish. So let's take a quick reading. Let this guy fire up. All right, we'll press start. Let it run its test. And we'll see where we end up on surface roughness. All right, results are in. So on this particular panel, we're sitting at 16.9. That's fairly fine. So this might be something that you consider close to an A-class finish for even like an automotive type tool for this level of finish and surface roughness level. Most aerospace tools we're talking about probably being in the range of 32 on average. Most often when it's coming off the machine in our rougher cuts, you're probably closer to around 60, 64 range, somewhere in there off the machine. So it's usually not a huge jump in time and effort to get to that 32. That's going to be acceptable for various efforts for layup tools or cure tools. So these are some basic steps in the finishing process. Over here on this end of the floor, we may do things like potting bushings, putting plumbing in, casters, drilling extra holes, deburring the tool. All those things will kind of happen on this end of the floor before we start getting into any of our more in-depth quality processes. And that usually starts with looking at a full evaluation of the tool, going through our statement of work, make sure all the features and requirements are met, but then also doing a full surface and structural validation of the tool, making sure it complies with any accuracy requirements for the features of the tool and the surfaces themselves. So to give you a quick demo of what that looks like, I'm going to bring Robert back in again, and he's going to do a laser scanning of, this is actually the cure tool for the same trim fixture we printed earlier and that Joe was machining. So this one's already been fully finished. We pulled high temperature laminates off this previously, but we're going to use this as the example. You can go ahead and see the surface finish on there. It's pretty smooth and shiny. And that's just with a tool sealer on it. No other post-finishing or sealers or coatings. This is just as you would lay up a laminate on top of the tool. So even here we're seeing great vacuum integrity even at high temperature up to 350 degrees or higher. So I'm going to pass over to Robert, and he'll show you kind of the data points we're capturing, and then maybe even do an overlay if we have time, and take it from there.
This is our Creaform laser scanner. It's 15 lasers, and it is very fast whenever. Let's see, I'm not referenced. Let's see if that'll work. There we go. Now it's picking up points. Okay. Yeah, we just got to keep you out of the way of the C-track behind you there. It's got to be able to see the scanner here in my hand. You can see the points showing up on the screen there.
All right, so gives you a quick demo of just how we capture the data. So from here, Robert's going to take this data, go into the inspector program, overlay it with the as designed geometries, and look for any deviations. And of course, we want to make sure that we can stay within spec for what the customer needs, and make sure that it's fully recorded and presented to our customer in our quality reporting. So every tool that leaves here has all documentation, all of our steps for checking specifications, features, surface roughness, and then of course dimensional accuracy across the entire tool itself. So all these things come to our customers as a fully developed package for their record keeping and for their analysis before we're allowed to ship the tool. So once we get through all these steps, essentially goes over to the customer, hopefully you, and you guys can go through, sign off on it, and it's off to your door. And something like this tool here, the trim fixture we printed today, from time of order receipt or the geometry that gets to our front door to a finished tool to your door, generally talking about 3 to 4 weeks, sometimes faster, really depends. But that's a good rule of thumb, somewhere in that small size, could be anywhere 3 to 4 weeks from time of PO, going through design processes, all the way through to a delivered tool. So let's go back down to the other end of the machine and kind of see where we started off in the beginning and see how our part's doing down there. It should be done. Okay, so let's go check out that part. So I think total print time on this part was right around 4 hours. So obviously we've moved around, but we tried to, through the magic of TV, show you both ends of the part in one go. So you see we're fully finished on this side. See a little house on the side of the part over here, if you come over to the side. So a little window in there helps with keep the weight down. And of course a little support header in the middle, which Robert designed for you guys earlier and showed you how that comes together. Come visit us at airtech3d.com. So we're ready to hear about your needs, both on materials and tooling, and we await your call and or email. We look forward to talking to you. Thanks.